Welcome to my presentation. University of Borishal, Department of Physics. Course title Electricity and Magnetism. Course code Physics 103. Presented to MD Ariful Islam Sir, Lecturer, Department of Physics, University of Borishal. My identity. Name Abu Sadat. Rule 20 Physics 017. Registration 171-01720. Session 2019-20. Former student of Department of Physics, University of Borishal. I am group leader of Group C. Group C. Group members: Shushmita Bishwash, Tauhiduzzaman Kais, Abu Sadat, MD Belal Hussain, Arman Rahman Rakib, Tawqir Ahmed, Shaikh Khan, Roshmi. Topics: A. Faraday's law of electromagnetic induction, Lenz's law, induction, self and mutual induction, transformer. B. Inductors, single loop RL circuit and time constant, energy stored in magnetic fields. Faraday's law of electromagnetic induction. This is most important and basic law of electricity and technology. We can say electrical technology is mainly based on this law. Operations of most basic component of electrical system like motor, generator, transformer and inductors are based on Faraday's law of electromagnetic induction. This law shows the relationship between electric circuit and magnetic field. Faraday's law of electromagnetic induction. Michael Faraday. Michael Faraday was an English scientist who contributed to study of electromagnetism. He found that when an electrical conductor is brought around the influence of magnetic field, it got attracted or detracted from the electric field. On this lesson, we shall learn about electromagnetic induction. The phenomenon of electromagnetic induction can be demonstrated by an experiment. Oren cylinder, south pole and north pole, wind an isolated copper wire on paper or Oren cylinder so as to form a coil in the form of solenoid. Connect the two ends of coil to a galvanometer and place a magnet close to it. Case 1. When the magnet is stationary, then the voltage is 0. Its north pole and south pole. The reading of galvanometer is 0 when the magnet is stationary. Case 2. When the north pole of the magnet is stationary, the pointer of galvanometer deflects towards the right when the north pole of the magnet is moved toward the solenoid. Case 3. When there is no motion of magnet, then voltage is 0, its north pole and its south pole. The galvanometer shows 0 reading when the motion of magnet stops. That proves that as long as the magnet keeps moving, current flows on the solenoid. Case 4. When the magnet is moved away, Wooden solenoidal, it's the south pole and go away from the magnetic field. If the magnet is moved away from the solenoid, current flows in opposite direction in the solenoid. Thus, the galvanometer deflects towards the left. Case 5. When the magnet is moved around the greater velocity, the deflection increases if the magnet is moved away from with greater velocity. Case 6. When the polarity of magnet is reserved. If the polarity of magnet is reserved and the magnet is brought close to the solenoid, then current flows in the opposite direction. The galvanometer accordingly turns towards the left. It's an experiment where we saw the galvanometer is moving from left to right and right to left when we connect a magnet, its north pole and its south pole. When we forward north pole to that position, the galvanometer moves left to right and oppositely vice versa. Faraday observed that current flows in the coil when there is a relative between the coil and magnet. If the current is positive, for example, when the magnet is pushed toward the coil, it will be negative when the magnet is pulled away from the coil. We can see that again. The direction of deflection in the galvanometer is reserved if the direction of motion is reserved. Factors leading to increased current in the coil by using a strong magnet: increasing the motion of magnet, increasing the area or the number of turns of the coil. Position of magnet and deflection in galvanometer. Magnet at rest. When the magnet at rest, no deflection in galvanometer. Magnet moves toward the coil. Deflection in galvanometer in the direction. Magnet is held stationary at same point near the coil. No deflection in galvanometer. Magnet moves away from the coil. Deflection in galvanometer, but in opposite direction. Magnet is held stationary at same position away from the coil. No deflection in galvanometer. Faraday's law of induction. Whenever there is a change in the magnetic flux linked with a coil, and electromagnetic force is inducted. Faraday's law of induction. Faraday's affecting the magnitude of the EMF. One charge in a magnetic flux to time in which the flux changes. The magnitude of the induced EMF is directly proportional to the rate of change of the magnetic flux linked with the coil. We can say that it's N into d phi by dt or ddt of phi. It is EMF value. Changes of magnetic flux is here d dt of phi in proportional to t. Its changes in magnetic flux to time in which the flux changes. Its EMF value is equals to n d phi by dt. The magnitude of the induced EMF is directly proportional to the rate of change of the electric flux linked with the coil. The direction of induced EMF depends on whether there is an increase or decrease in the magnetic flux. So, Faraday's first law: whenever a conductor is placed in the varying magnetic field, electromagnetic fields are induced, known as induced EMF. If the conductor circuit is closed, a current is also induced, which are called induced current. Faraday's second law: the induced EMF in a coil is equal to the rate of change of flux linkage. Here, the flux is nothing but the product of the number of turns in the coil and flux connected with the coil, and so on. At last, please pardon my mistake as I am new. Thank you.